In this video, we're going to talk about kinetic energy and potential energy. But let's begin our discussion with kinetic energy. What is kinetic energy? Well, think about the word kinetic. What does that tell us, kinetic? Kinetics has to do with motion. So kinetic energy really represents energy in motion. Anything that moves has kinetic energy. So if you have a ball moving at 5 meters per second, it has kinetic energy. If you have a block that's at rest, it's just sitting on the ground doing nothing, it has no kinetic energy. So anything with mass and speed has kinetic energy. The formula for it is Ke is equal to 1/2 mv squared. So kinetic energy depends on the mass and the speed of the object. The units for m is the kilogram. The units for speed typically is in meters per second. And if you use those units, the kinetic energy will be in joules. Now, a typical question that you might see on a physics exam would be something like this. If you double the mass of an object that's moving, what happens to the kinetic energy? And what about if you double the speed? How do you answer those types of questions? So let's talk about it. First, let's rewrite the formula. Ke is equal to 1/2 mv squared. And notice that m is raised to the first power. If you don't see a number there, it's a 1. Now, if we double the mass, the kinetic energy will double. What you can do for a question like this is replace everything with a 1 except the stuff that's changing. So we're only changing the mass. So we're going to ignore the 1/2. We're going to replace m with 2. We're not changing the speed, so we're going to put a 1. This will give us 2. This tells us that the kinetic energy doubles. Now, what if we double the speed? We're not changing the mass. We're going to ignore the constant, but we are doubling the speed. If you replace v with a 2, 2 squared is 4. So this tells us that the kinetic energy quadruples if you double the speed. Now, based on that, here's another question. Let's say if you increase the mass by a factor of 3, and if you quadruple the speed, if you increase it by a factor of 4, how much will the kinetic energy change from its original value? So in this case, once again, we're going to ignore the 1/2. We're going to triple the mass, quadruple the speed. 4 squared is 16. 3 times 16 is 48. So the kinetic energy will increase by a factor of 48. And that's a typical question that you might see on a physics exam, but that's how you can answer it. At least that's a shortcut method of answering those types of problems. Now, what about potential energy? What is potential energy? You could think of this as a form of stored energy. It's basically the energy due to position. So let's say this is the ground, and we have object A and object B. Which one has more gravitational potential energy? Now, object B is at a higher position relative to the ground. So object B has more potential energy than object A, assuming, of course, that they have the same mass. So potential energy is really energy due to position. Object B can fall a greater distance than object A, and so it has more potential energy. The formula for gravitational potential energy is mgh, where m is the mass in kilograms, g is the gravitational acceleration, which is in meters per second squared, and h is the height above ground level, which is typically in meters. The gravitational acceleration is 9.8 meters per second squared. So these are the two formulas you need to know. This one for gravitational potential energy, and this one for kinetic energy. And that is a 2. It's a terrible looking 2, but it's a 2. Now let's say this is the ground, and we have a ball, let's say it's a 10 kilogram ball, and it's currently 50 meters above the ground. So at this position, let's call it position A. How much potential energy does the ball have at this position? So to calculate it, we could use this formula, mgh. So we have a mass of 10 kilograms, the gravitational acceleration is 9.8, and the height is 50. So let me pull out a calculator. And so this is going to be 10 times 9.8 times 50. So the gravitational potential energy is 4,900 joules. Now, let's say if we release the ball from rest, so it begins to fall. Just before it hits the ground, we'll call that position B. What is the kinetic energy at position B? What would you say? It's important to understand that as the ball falls from position A to position B, its potential energy is being converted to kinetic energy. Why do we say that? Well, as it goes from A to B, its position, or rather its height relative to the ground, is decreasing. And as the height decreases, its potential energy is decreasing. However, as it falls, it's accelerating towards the ground. And so it's speeding up, it's moving faster and faster. So as the speed increases, the kinetic energy is increasing. So the net result is that as the ball falls from position A to B, the gravitational potential energy is decreasing, but the kinetic energy is increasing. So one form of energy is being converted to another. At position B, just above the ground level, basically the potential energy is zero. So at that point, all of the potential energy has been converted to kinetic energy. So at position B, let me just get rid of this, the kinetic energy is going to be equal to 4,900 joules, this number. So the potential energy at point A is equal to the kinetic energy at point B when it can fall no more. So B is the lowest position that the ball can reach. At that point, all of the potential energy has been converted to kinetic. Now here's another question for you. At position B, just before the ball touches the ground, how fast is it moving? How can we find the answer to that question? Well, we could use this formula. Kinetic energy is equal to 1/2 times the mass times the square of the speed. And so we could replace Ke with 4,900 joules, and we have the mass. It's 10 kilograms, and so we could solve for V. Half of 10 is 5. So we have 4,900 is equal to 5V squared. And so at this point, it's all math. Our next step is to divide both sides by 5. 4,900 divided by 5 is 980. And so that's equal to V squared. Next, we're going to take the square root of both sides. And the square root of 980 is approximately 31.3. So the object is going to be moving at a speed of 31.3 meters per second just before it hits the ground. And so using the principle of conservation of energy, you could answer questions like these. Now for those of you who want more difficult problems in terms of kinetic energy, potential energy, work, power, and stuff like that, check out the links in the description section below in this video. And I'm going to post some other videos that can help you with harder problems if you need help in that area. So feel free to take a look at that when you get a chance. Now there are some other forms of potential energy. Another one that you might see in the first semester of physics is something known as elastic potential energy. Now some physics textbooks, instead of using PE for potential energy, you might see a capital U symbol. And the formula for elastic potential energy is 1/2 kx squared. So here's an example of when you would have a situation that has elastic potential energy. Let's say if you have a spring. Now, if you apply a force, you can compress the spring. And once you release that force, that energy that you use to compress the spring has been stored. And once you release the spring, that spring will have the tendency to go back to its original length. So this is Fa, the force that you apply, and Fr is the restoring force. It's the force that wants to bring the spring back to its position of equilibrium. Now let's talk about this equation, 1/2 kx squared. K represents the spring constant, which is measured in newtons per meter, and x represents how far the spring has been compressed or stretched from its equilibrium position. So the sign of x really doesn't matter because once you square it, it's going to be positive. But it's how far it is from its natural length, and it's typically in meters. Now to understand the spring constant tells you how stiff or how loose the spring is. So for example, let's say if we have spring 1 with a spring constant of 100 newtons per meter versus spring 2, which has a spring constant of 500 newtons per meter. Which one is loose and which one is more stiff? This spring is going to be more loose because it's very easy to stretch or compress it. This one is going to be more stiff because it's harder to stretch or compress it. But let's think about what this number actually means. 100 newtons per meter. What does that mean? It means that for this particular spring, a force of 100 newtons is required to stretch or compress the spring by a distance of 1 meter. Now the second spring requires 5 times the amount of force. So you need 500 newtons of force to stretch or compress the spring by 1 meter. And that's why we could say that this spring is more stiff, because it's much harder to stretch or compress the spring by the same amount of distance. So this is another form of energy that you may or may not have to know, depending on what class you're taking. So elastic potential energy, it's another form of stored energy. And there's other forms of potential energy like chemical energy, the energy stored in chemical bonds. You also have the electric potential energy, the energy stored between a charge based on its position in an electric field. And I'm not going to go into those topics, but just understand that there's many different forms of potential energy. So that's basically it for this video. If you like it, feel free to subscribe. And don't forget to check out the links in the description section below if you want access to harder problems relating to this topic. Thanks again for watching.